Hello everyone, in this video I'll be showing how to find an electric field outside and inside a uniformly charged spherical shell. So for that, let's start by drawing a figure. A spherical shell with a uniformly positive charge on the surface and with a total charge of Flux. So it has a center O with a radius R. So firstly we need to find an electric field outside the shell. So let's assume that we need to find an electric field at point P outside the surface of the electric shell. So let's take a point P somewhere here. And point P is at a distance small r from the center O. So let's apply a Gauss law in this point P by drawing a Gaussian surface. Take a small area element ds at the point P, ds vector, and say the direction of the area element is perpendicularly outward the surface. And let's say this area element possesses an electric field E vector. If E is the electric field at point P, then the small electric flux crossing through the small area element ds is given by d phi is equal to E ds, which is coming from the formula of electric flux, which is phi is equal to E ds. But in this case, since it is a small amount, so we took it as d phi. So d phi is equal to E ds, and let's take this equation as equation number 1. And moving on to the next step, which is we need to find a total electric flux crossing the Gaussian surface using Gauss Law. So, total electric flux which is phi is equal to closed surface integral of d phi, closed integral surface of E ds. E ds because we are replacing the value of d phi which we got in equation number 1. And since E is a constant here, let's take E outside, which will become as E closed surface integral of ds. And by simplifying further, which implies phi is equal to E into 4 pi r squared. 4 pi r squared because the value of closed surface integral of ds is equal to s, and s is equal to 4 pi r squared, which is the surface area of the sphere. And so let's take this equation as equation number 2. And again we need to find a total electric flux crossing the Gaussian surface using another Gauss law, which is again phi is equal to q by epsilon naught. And let's term this equation as equation number 3. Now we can simply find out the electric field outside the spherical shell by comparing the value of phi in equation number 2 and equation number 3. E into 4 pi r squared equal to q by epsilon naught. Here, E into 4 pi r square is the value of phi in equation number 2, and Q by epsilon naught is the value of phi in equation number 3. And by simplifying further, we get E is equal to Q by 4 pi epsilon naught r square. So let's take this equation as equation number 4. Here, equation number 4 gives us the electric field outside a uniformly charged spherical shell. The next part of the derivation, which is to find an electric field inside a spherical shell. So for that, let's draw a similar type of figure. Since we need to find an electric field inside the shell, let's take a point P somewhere inside here, which is at a distance small r from the center O. And also let's consider a Gaussian surface passing through. As we can see that there is no charge inside the surface, but only outside the surface. So it basically means Q is equal to 0. Q is equal to 0. So we can apply this Q is equal to 0 in the previous equation, equation number 4, and we can find the electric field inside the spherical shell. So this one, equation 4 implies E is equal to 0 by 4 pi epsilon naught r square. Since 0 because there is no charge. Charge is 0. Therefore, E is equal to 0. And this is the required expression for electric field inside the spherical shell.